Hello learners, as I have already discussed in the introductory video of this course that this course is basically deal with the basics of quantum mechanics. The main focus of this course will be on the two basic concepts of quantum mechanics. One is the quantization of energy and another one is the probabilistic nature of quantum mechanical phenomena. This course actually is of 2-week course. Each week will have 6 lectures as you can see in this slide. During the first week, we will discuss the basic concepts like wave particle duality and physics that demand the quantum mechanics and some of the phenomena that actually deal with the quantum mechanics or the phenomena that can only be explained with the help of quantum mechanics like black body radiation, photoelectric effect and Compton effect and all that. In the second week, we will discuss the de Broglie wavelength and Heisenberg uncertainty principle. And in the last, we will discuss the wave function and probability density nature of quantum mechanics and the Schrodinger wave equation. The objective of this course is to transform the knowledge of basic principle of quantum mechanics and its conceptual formulation. By the end of this course, the learners will be equipped with the fundamental understanding and insight into the quantum mechanical contribution of modern applications. Let us start with a very vibrant question, that is, why quantum mechanics? Or what is quantum mechanics? Actually, classical mechanics is the mechanics that deal with the macroscopic phenomena. Macroscopic means all those phenomena or all those particles that can be seen by the human senses. While the quantum mechanics is the physics that deal with the microscopic phenomena or microscopic particle, like the motion of electron in a shell. Quantum mechanics helps to explain the physics of number of weird physical phenomena like black body radiation, photoelectric effect, Compton effect, atomic spectroscopy, uncertainty principle, wave particle duality, quantum tunneling, electron diffraction. These are some phenomena. The list of these experiments or the experimental observations are too large. Some of the most popular experimental observations are listed here, which actually forced the science community to introduce a new type of physics because classical physics was not capable to explain the physics behind the cause of these phenomena. Some of the physics, if we want to discuss some of the physics that actually demand the quantum mechanics are like the existence of atom or why the atom disintegrate in nanoseconds is not integrating in nanosecond. Actually, as we all know, in an atom, electron circulate around its nucleus, and according to this is called wiggling, and according to the electromagnetic theory, when a electron revolve around a positive charge, it will always be a accelerating motion, and accelerated electron will always tends to release the energy, and due to this loss of energy, electron must merge ultimately inside the nucleus. Means the existence of nucleus or the circulating electrons separately should not be there, but it is there. Means atom is exist and electron is frequently or without losing any amount of energy is circulating the nucleus. Classical mechanics do not have the answer of this circulating electron around the nucleus. The cause behind the circulation of electron or the existence of electron in its shell. Why don't hot objects emit more ultraviolet light than they do? Classically, it was supposed that when a object is heated at a certain temperature, it must release an infinite wavelength, infinite energy under the ultraviolet region, which is called also called the ultraviolet catastrophe, the concept of ultraviolet catastrophe. But this is also not so. Every atom releases a maximum amount of energy at a maximum wavelength or maximum frequency. None of the atom in this universe can release infinite amount of energy at infinitely large frequency or infinitely small frequency or the ultraviolet radiation. Another one is why the red light is incapable of knocking electron out of the certain material, no matter how bright it is, yet blue light could readily do so at the modest intensity. That is photoelectric effect. Means a high frequency radiation are capable to release the electron from the metallic surface, while the low frequency radiations was not capable to release the electrons from the surface. Although at that time the people do not have the concept of frequency can be treated as energy, as an energy. So that's why they are not capable to understand why the red color is not capable to release the electron from the metallic surface. On the other hand, blue color is capable. What caused the next one is was what caused the spectra of an atom to certain discrete lines? Means when the when the science community observed the spectrum or the radiation emitting from an atom, they found that the spectrum was not continuous, as we all observe. While every atom release a certain amount of frequency only. That is, this is called the discreteness of spectra. And this is also the characteristic nature of every atom. Each atom has a distinct fingerprint and only a small set of optical frequencies could be emitted or absorbed by that atom. This was not also possible to explain with the classical mechanics. Like hydrogen atom that only have one electron and one proton emits several wavelengths. The science community was very surprised how we can explain the physics behind the cause of these phenomena. Let us, before giving the answer of all these questions, let us discuss the concept of wave particle duality, which is, I think, one of the most popular concept of quantum mechanics. Means, what does it mean? Wave particle duality means a wave can be treated as a particle and particle can also be treated as a wave. Actually, this concept of wave particle duality was coined back around in 1600 when Christian Huygens first proposed the concept of wave for the radiation. He said that we can treat wave as a we can treat radiation as a wave. Before this, the wave was treated as a ray, or ray theory of light was much popular. And first, Huygens proposed that the light can be treated as a wave. And as you know, as you all know, wave is nothing. It is the disturbance of medium's particle whenever the energy is allowed to pass through a medium. it will disturb the medium's particle, and if we trace the locus of all those vibrating particles of medium which are in the same phase, then that path will be treated as a wave. So radiation, according to Huygens, each radiation have the tendency to vibrate the medium's particle and can be treated as a wave. Around in 1700, Isaac Newton proposed a theory that is part wave or the radiation can also be treated as a particle. Although in that era, that theory was not much get much popularity, but in his theory, Newton says that radiation can also be treated as a particle. And those particles are known as corpuscles, and those tiny corpuscles, he says that these corpuscles are sensitive to the color. Whenever these corpuscles fall over the eye of or retina of a human eye, they give us the sense of the color, and these particles are actually responsible for the vision of a human body. But they did not get much support for his theory, as the Huygens get a wonderful support for the wave theory, for his wave theory. In 1900, Max Planck gave a breakthrough concept of particle nature of light. He said, Newton said that particle light is made up of particle, and those particles are color sensitive. While Planck said that light can suppose to be made up of tiny particles, not the particle, while the energy packets. Light is an energy, and he said that this energy is not continuous. Continuous means it is not possible to extract any amount of energy from a source of energy, while we can extract only a certain or the discrete amount of energy if we know the minimum unit of energy. Then the extracted energy or the supplied energy will always be the integral multiple of that minimum unit. And he termed that minimum unit as a quantum or the photon or the packet of smallest amount of energy packet is known as photon. And whatever the energy either we are emitting or either we are receiving or we are releasing will always be the integral multiple of that minimum amount of energy. Interestingly, just interestingly, just 23 years later, in 1923, de Broglie proposed the concept of particle nature of wave again, of wave nature of particle. Means every particle can be treated as a wave. He termed it as the material wave. He said that whenever a particle is in motion, it will always release a certain amount of energy behind it, and this energy is also the characteristic nature of this particle, and this is known as the matter wave. Undoubtedly, this matter wave is significant for the microscopic particles. Macroscopic particles do not have a significant matter wave. We will discuss it later on. Means the idea of duality is rooted in the debate over the nature of light and matter dating back to 1600, when competing theory of light were proposed by Huygens and Newton. And around 300 years later, the same idea comes again. Planck proposed the concept of particle nature of light, while de Broglie proposed the concept of wave nature of particle. That's why this is called wave particle duality. Means every radiation can be treated as a particle as well as a wave to explain the certain phenomena. This is all about the first two lectures of this course. The next four lectures, we will discuss the certain phenomena associated with the wave nature of light.